Welcome to Probability Theory and Statistics. Today we are going to explore one of the most powerful ideas in all of mathematics, the standard error of the sample mean. If you have ever wondered how scientists can predict the outcome of an election by asking just a few thousand people, or how we know a new medicine works without testing it on the entire world, you are in the right place. We are going to build this concept from the ground up. So even if you are completely new to statistics, you will understand exactly how and why this works. Let us dive in. To understand what the standard error is, let us start with a simple analogy. Imagine you are cooking a massive pot of vegetable soup for a huge party. This entire pot represents our population, which is the complete set of everything we want to study. You want to know the average number of carrots per bowl. Instead of counting every single carrot in the giant pot, you scoop out one ladle of soup to check. That single ladle is your sample, and the average number of carrots in that ladle is your sample mean. If you pour that ladle back and scoop another one, you will probably get a slightly different number of carrots. The standard error tells us exactly how much those ladle averages will bounce around from scoop to scoop. Now that we have our soup analogy, let us look at the formal statistics. Why does this bouncing around matter? Because in real life, we usually only get to take one sample. When we take many different samples from a population, each sample gives us a slightly different average. If we plot all of those sample averages on a graph, they form their own bell-shaped curve, which we call the sampling distribution. The standard error is simply the standard deviation of this specific curve of averages. It tells us the typical distance between the average of our single sample and the true average of the entire population. A smaller standard error means our sample average is very close to the true population average, making our estimate highly accurate. This brings us to the mathematical heart of the topic. How do we actually calculate this bounce? The formula for the standard error is the population standard deviation divided by the square root of the sample size. Let us break down every symbol. SE stands for the standard error itself. The Greek letter sigma represents the standard deviation of the original population, which tells us how spread out the individual items are. Finally, n represents the sample size, which is the number of items we measured. Notice that n is inside a square root in the denominator. This reveals a beautiful truth. To cut your error in half, you cannot just double your sample size. You must quadruple it. As the sample size increases, the denominator grows and the standard error shrinks. Before we look at where this formula comes from, let us see it in action with a concrete example. A factory manufactures light bulbs. From years of historical data, the factory knows that the lifespan of individual light bulbs has a population standard deviation of 120 hours. A quality control inspector takes a random sample of 36 light bulbs to test their average lifespan. We need to find the standard error for this batch. We start by writing down our formula. We are given the population standard deviation sigma, which is 120, and the sample size n, which is 36. We substitute these known values into our equation, placing 120 in the numerator and the square root of 36 in the denominator. Continuing with our calculation, we need to simplify the fraction. We calculate the square root of the sample size in the denominator. The square root of 36 is exactly 6. This step simplifies the bottom of our fraction, leaving us with a simple division problem, 120 divided by 6. Finally, we perform the division to get 20. The standard error of the sample mean is 20 hours. What does this mean physically? It means that if the inspector takes many different samples of 36 bulbs, the average lifespan of those samples will typically bounce around the true factory average by about 20 hours. This gives the inspector a clear, reliable margin of error for their test. Now that we have used the formula successfully, let us understand exactly where it comes from. We will derive it step by step using the basic rules of probability. Let us assume we have a large population with a true average, denoted by mu, and a true variance, denoted by sigma squared. We draw a sample of size n, meaning we pick n individual items at random. We will call these items x1, x2, all the way up to xn. To find the sample mean, which we write as x bar, we simply add all these individual items together and divide by the total number of items, n. This is our starting equation. This chunk of the proof is where the magic happens. We want to find the variance of this sample mean, so we apply the variance operator v to both sides of our equation. Now we must use a key rule of probability. When you multiply a random variable by a constant number, the variance is multiplied by that constant squared. In our equation, the constant is the fraction 1 over n. When we pull this fraction outside the variance function, it must be squared, becoming 1 over n squared. This mathematical rule is exactly why the sample size ends up having such a powerful, non-linear effect on the final error. Moving forward, we look inside the parentheses. Because each item in our sample is chosen randomly and independently from the others, the variance of their sum is simply the sum of their individual variances. Since every item comes from the exact same population, every single x has the exact same variance, which is sigma squared. Therefore, we are simply adding sigma squared to itself n times. Mathematically, adding the exact same value together n times is identical to multiplying it by n. So the sum inside the parentheses simplifies beautifully to n times sigma squared. We are now ready to combine the inside and the outside of our expression. We are at the final steps of our derivation. We have an n in the numerator and an n squared in the denominator. We can cancel out one n from both, leaving us with the variance of the sample mean equal to sigma squared divided by n. Finally, remember that the standard error is defined as the standard deviation of the sample mean. Because standard deviation is always the square root of variance, we simply take the square root of both sides. The square root of sigma squared becomes sigma, and the square root of n becomes root n. This gives us our final proven formula. So we have proven that the formula holds. This brings us to a visual understanding of what we just calculated. Look at the diagram on your screen. The wide, flat curve represents the raw population distribution. Notice how spread out it is, indicated by the large arrow for sigma. Individual items can be very far from the center. Now look at the tall, narrow curve inside it. This represents the sampling distribution of the mean. Because we are taking averages of multiple items, the extreme highs and lows cancel each other out, causing the sample means to cluster tightly around the true center. The standard error is simply the width of this narrow curve. Before we conclude, let us look at a more advanced application. The factory manager from our previous example is not satisfied with a standard error of 20 hours. She demands that the standard error be reduced to exactly 10 hours. Assuming the population standard deviation remains 120 hours, how many light bulbs must the inspector test? In this scenario, we know the desired standard error and the population spread, but the sample size is unknown. We begin again with our fundamental formula. We substitute the target standard error of 10 on the left side and the population standard deviation of 120 on the right. Our goal is to isolate the unknown variable n. Continuing with our algebra, we need to get n out of the denominator. To isolate the variable, we multiply both sides of the equation by the square root of n. This algebraic move cancels out the denominator on the right side and shifts the unknown variable to the left side. Next, we divide both sides of the equation by 10. This removes the number 10 from the left side, leaving the square root of n completely by itself. The right side becomes a simple fraction of 120 divided by 10. Simplifying this fraction gives us a clean result of 12. We are almost there. For our final steps, we see that the variable is isolated, but it is still trapped inside a square root. To remove the square root, we must perform the opposite mathematical operation. We square both sides of the entire equation. Squaring the square root of n simply leaves us with n. Squaring the number 12 on the right side gives us 144. The inspector must test 144 light bulbs to achieve the desired precision. Notice that to cut the error in half from 20 to 10, we had to multiply the sample size by 4, going from 36 to 144. This perfectly illustrates the square root relationship. Now that we have mastered the calculations, let us zoom out and understand why this matters in the real world. The standard error is one of the most critical concepts in all of scientific research. In real life, we almost never know the true average of an entire population because it is too expensive or impossible to measure every single item. Whether we are testing a new medical drug or checking the safety of drinking water, we are forced to rely on a single sample. The standard error acts as a mathematical safety net, telling us exactly how much we can trust that sample. Without it, we would have no way of knowing if our result is accurate or just a random fluke. We have covered a lot of ground today, so let us review the key takeaways. First, remember that the standard error measures the reliability of a sample average. It tells you how much your sample mean is likely to bounce around the true population mean. Second, mathematically, it is the standard deviation of the sampling distribution. Third, the formula divides the population standard deviation by the square root of the sample size. And finally, because of that square root, increasing your sample size always makes your estimate sharper but with diminishing returns. You have now unlocked the core concept that bridges the gap between a small sample and a massive population. Great job today.